Welcome to the Deep Dive, where we cut through the noise and get you straight to the insights. Today, we're diving into one of the most intriguing tensions in the world of digital money. It's this question. How do you build a system you can trust, one that's publicly verifiable, without completely exposing everyone's financial life?
Right, because most digital currencies, as you know, they rely on these public ledgers, blockchains.
Exactly, and every single transaction is visible. Now, that transparency, it has its benefits, sure, for verification and trust.
But it definitely comes at a cost. Your sensitive financial information is just out there in the open.
It's a fundamental paradox, isn't it? We need to ensure funds aren't duplicated or faked, absolutely.
But privacy, well, that's a core expectation most people have with their finances, like in the traditional system.
Trying to reconcile those two things, transparency and privacy in a digital world, that's a really complex challenge.
It really is.
And that's exactly why today we're taking a deep dive into Monero, or XMR. It's a cryptocurrency that's been uniquely engineered with privacy right at its absolute core, from the beginning.
Yeah, it's a truly fascinating example. It shows how cutting-edge cryptography can be used to build a digital money system that, really prioritizes confidentiality.
And our understanding for this deep dive, it comes straight from a pretty comprehensive technical guide called Zero to Monero, first edition.
Right. So our mission today is to unpack Monero's core privacy mechanisms. We want to help you grasp the technical innovations that make it work.
And understand how these translate into real-world financial confidentiality for you. Think of this as your shortcut to being genuinely well-informed about Monero's unique approach.
Okay, let's unpack this then.
So let's start with the problem Monero really sets out to solve, this public ledger issue. Most digital currencies, Bitcoin being the classic example, they live on a blockchain, that public distributed record.
Where every transaction is recorded right there in plain sight. Which, again, makes verifying things super easy. Great for preventing fraud.
But the downside, as you can probably imagine, is your entire transaction history becomes public knowledge. Every payment, every receipt, visible to anyone who cares to look.
And it actually goes further than that, doesn't it? Even systems that try to obfuscate transactions, maybe using temporary addresses or something.
Yeah, those often fall short.
Exactly. With sophisticated analytical tools, it's often possible to trace the flow of funds anyway. You can link seemingly anonymous activity back to the real senders and receivers.
So what looks private on the surface might not stay private for long. It can often be de-anonymized.
Which brings us to Monero. Here's where it gets really ingenious, I think. Monero tackles this head-on. It takes a fundamentally different approach.
Okay, how?
Well, first, for every single payment you receive, Monero generates a unique one-time address just for that transaction.
So instead of reusing your main address over and over?
Right. Each transaction output goes to what looks like a completely new, unrelated destination on the blockchain.
So an outside observer looking at the blockchain, they just can't link those transactions back to your main public address.
Exactly. It breaks that link completely.
Okay, that's recipient privacy. What about sending?
That's just the start. When you send funds, Monero uses this clever technique called ring signatures.
Ring signatures. Okay, what are those?
Imagine your transaction being cryptographically mixed in with several other unrelated transactions from different people, sort of like hiding in a crowd.
Okay.
The network can verify that someone in that group, that ring, definitely authorized the transaction with a valid private key.
Yeah.
But it's computationally impossible to tell which specific person in the ring it was. The actual sender remains ambiguous within that group.
Wow. So that makes tracing the origin of funds effectively impossible?
Pretty much, yeah. Extremely difficult, bordering on impossible with current tech.
And it doesn't stop there, right? You mentioned amounts, too.
Correct. On top of hiding senders and recipients, Monero also conceals the actual transaction amounts.
How?
They're hidden behind these complex cryptographic constructions. It renders the precise flow of currency completely opaque to anyone except the actual sender and receiver.
So the end result is privacy isn't just an option, it's baked in. Mandatory.
Exactly. Privacy by default, built into every single transaction.
The real genius here, though, is how Monero pulls this off. It's this sophisticated cryptographic toolkit.
Yeah, absolutely. At its foundation, a lot of Monero's cryptography relies on elliptic curve cryptography, ECC.
Okay, ECC, I've heard of that.
Think of it as a super secure mathematical lock. Monero uses a specific type chosen for efficiency, called ED2551 HUN, The core idea, the thing that makes it work, is that it's easy to calculate a public key from a private key.
But practically impossible to go the other way around, to get the private key from the public one.
Precisely. That one-way function, the difficulty of solving the discrete logarithm problem on these curves, is the bedrock of Monero's security and privacy.
Okay, so ECC is the foundation. But back to the amounts. If they're hidden, how does the network even prove that the inputs of a transaction actually equal the outputs plus fees? It feels like. Like magic. How do you know the sum without seeing the numbers?
It does seem a bit like magic, doesn't it? But the solution is actually pretty elegant. It lies in something called Pedersen commitments.
Pedersen commitments. Okay, break that down.
Think of them like sealed envelopes containing cash. You can't see the amount inside each envelope.
Right.
But, crucially, these commitments are additively homomorphic. That means you can perform addition on the envelopes themselves. If you add the commitments for the inputs together and add the commitments for the outputs and fees together,
The math still has to check out. The total commitment for inputs must equal the total commitment for outputs plus fees.
exactly. You can mathematically prove that inputs, outputs, fees equals 0 using the commitments without ever revealing the actual values hidden inside. It ensures no money is created or destroyed out of thin air.
And there's a key component to these commitments that makes the privacy really strong, isn't there? Something called a blinding factor.
Yes, absolutely crucial. A blinding factor is basically a large random number that gets added into the commitment along with the actual amount.
Why is that so important?
It provides what's called information theoretic privacy. It means that even an attacker with theoretically infinite computing power couldn't figure out the amount.
Infinite power. How?
Because for any given commitment value you see on the blockchain, there are countless possible combinations of the real amount and the random blinding factor that could have produced it. As long as that blinding factor stays secret, the amount is perfectly hidden.
That sounds incredibly robust. Okay, but wait. If amounts are hidden and you can prove inputs equal outputs, what stops me from creating a transaction where I send myself, say, -10 Monero from an input? The Pedersen commitments would still balance to 0, right? I'd essentially be creating money.
That's a very sharp question. That raises a really important point. Just proving the sums match isn't enough. You also need to prove the amounts aren't negative.
So how does Monero handle that?
It addresses this using another clever piece of cryptography, Borromean ring signatures, which are used here to create range proofs.
Range proofs, meaning they prove the amount is within a certain range.
Exactly. For every single output in a transaction, Monero includes a cryptographic proof confirming that the hidden amount falls within a specified non-negative range, usually something like between 0 and 2 to the power of 64 minus 1 atomic units.
Without revealing the actual amount.
Without revealing the actual amount. It does this by essentially committing to each individual bit of the amount's binary representation and proving they form a valid number in the allowed range.
Wow.
And these signatures are also non-linkable, which means they don't create any new ways to trace or link transactions based on the amounts. So you prevent artificial money creation and maintain amount confidentiality.
Okay, so we've covered these incredible underlying crypto mechanisms. Let's shift gears a bit. How do Monero transactions actually work in practice from a user's point of view? Starting with the keys. I heard Monero does keys differently.
It does. Unlike many cryptocurrencies, where you just have one main private-public key pair, Monero users actually have two distinct pairs. There's a private and public view key and a private and public spend key.
Two sets. Why?
This separation is really crucial for offering granular privacy and control. Your view key, specifically the private view key, lets you scan the entire blockchain and identify which transactions are actually yours. It lets you see your incoming funds and decrypt their amounts.
Okay, so you can see what you received.
Right. And this is super useful if you want to, say, give a trusted third-party access to view your transaction history, maybe an auditor, or for tax reporting. You can give them your view key.
But they can't spend your money with just the view key.
Exactly. They get read-only access to your incoming transactions. You can see what you receive, but they absolutely cannot touch or spend your funds.
That power comes from the spend key then.
Precisely. The private spend key is what actually authorizes the spending of your Monero. It signs the transaction, proving you own the funds. So you maintain full control over spending while having the option to selectively share visibility. It's a powerful privacy feature.
That makes sense. And building on that, you mentioned those one-time addresses earlier for receiving funds. How are those generated?
Yeah, so when someone sends you Monero, a unique one-time public key is generated just for that specific transaction output. This uses a clever cryptographic process, kind of like a Diffie-Hellman key exchange, involving the sender's randomness and your public view and spend keys.
Okay, so the sender uses my public keys to create a unique address only I can access.
Essentially, yes. The result is that even if someone knows your main public Monero address, the one you might share openly, they cannot look at the blockchain and figure out which transactions were actually sent to you.
Because each incoming payment goes to what looks like a totally different, unrelated address.
Exactly. It's like having a brand new, unique mailbox appear just for each individual letter you receive, even though they all ultimately end up at your house, under your control via your private keys.
That's brilliant for recipient anonymity,
Yeah.
but managing potentially hundreds or thousands of these unique addresses sounds like it could get really complicated for the user, doesn't it?
That's a fair point, and that's where sub-addresses and integrated addresses come into play. They enhance the usability significantly.
Okay, tell me about sub-addresses.
From your single main wallet address and its keys, you can generate a practically unlimited number of sub-addresses. Think of them as derived addresses linked to your main account.
How is that useful?
It's incredibly useful because you can give out a different sub-address for each payment you expect to receive without revealing your main address or linking the payments together publicly.
Oh, I see. So a business could give each customer a unique sub-address.
Exactly. Or you could use one for donations, one for a specific online service, etc. From an outside observer's perspective on the blockchain, these sub-addresses look completely distinct and unrelated.
But all the funds still come into my main wallet.
Yes, you manage all the funds received at any of your sub-addresses from your single wallet using your main private keys. An observer cannot tell that these multiple sub-addresses belong to the same person unless they can solve the underlying elliptic curve discrete logarithm problem, which is computationally infeasible.
Very cool. And integrated addresses, you mentioned those too.
Right. Integrated addresses are a way to bundle a short payment ID directly into a Monero address format.
A payment ID, like for an invoice number.
Precisely. It's useful for merchants or exchanges who need to associate incoming payments with specific customers or orders. The clever part is that this payment ID isn't stored in plain text on the blockchain.
How is it hidden then?
When the transaction is created, the payment ID is scrambled using a simple XOR operation with a shared secret derived from the transaction keys. This means only the sender and the recipient can easily extract and read the original payment ID.
So it helps the recipient organize funds without broadcasting that ID publicly? Neat.
Yeah, balances utility with privacy.
Okay, so all of this incredible privacy technology, the ring signatures, the hidden amounts, the one-time addresses, it all comes together in what Monero calls ring confidential transactions, or ring CT.
Yes, ring CT is basically the protocol that combines ring signatures for sender anonymity with confidential transactions using Pedersen commitments and range proofs for amount anonymity.
And this is now the standard. You can't not use it.
That's right. Ring CT became mandatory for all network transactions quite some time ago. Privacy is the default, not an option you have to remember to turn on. Everyone benefits from the same strong privacy protections.
Have there been different versions or improvements to ring CT?
Oh yes, Monero development is ongoing. There have been refinements. For instance, the original ring CT had different types, but the current standard, often referred to generally as ring CT, incorporates improvements like MLSAG signatures. And they designed ways to handle transactions with multiple inputs efficiently.
How so? What was the challenge with multiple inputs?
Well, one approach could be to aggregate everything into one giant signature. But a cleverer approach they adopted involves signing each input individually within the ring structure.
Why is that better?
It decouples the inputs. This is a really crucial insight for resilience. It means if, hypothetically, the anonymity of one specific input used in your ring was somehow compromised later on.
The other inputs you mixed with remain anonymous. It doesn't unravel the whole transaction's privacy.
Exactly. It contains the potential damage, making the overall system much more robust. It shows a deep commitment to providing practical, resilient privacy.
Okay, but the fundamental question for any cryptocurrency, especially one this private, how do you prevent double spending? If you can't see who sent what or how much, how do you stop someone spending the same money twice?
That's where key images play their absolutely critical role. They are part of the ring CT signatures, specifically the MLSAG signatures used now.
Key images.
How do they work? Remember, the ring signature proves someone in the ring owned the funds being spent without revealing who. The key image provides the link needed for double spend detection.
How?
Each specific output, UTXO you own, has a unique key image associated with it, derived mathematically from your private spend key in the output itself. When you create a transaction to spend that output, its unique key image is included in the transaction data and recorded on the blockchain.
Okay, so the key image goes on the blockchain.
Now, here's the crucial part. Because the key image is derived directly from the specific output being spent if you try to spend that same output again in another transaction.
It will generate the exact same key image.
Exactly. And the Monero network keeps track of all key images that have been spent. If a new transaction comes along containing a key image that's already on the list,
The network immediately knows it's a double spend attempt and rejects the transaction.
bingo, it links the two attempted spends together to prevent the fraud, but, and this is key, it still doesn't reveal which member of the ring was the actual signer. It perfectly balances security against double spending with sender anonymity.
That is remarkably clever. It solves the double spend problem without compromising the core privacy feature.
It's one of the core innovations, really.
And what about transaction fees? Are they also hidden or part of this commitment scheme?
Transaction fees are stated clearly in the transaction data. They aren't hidden in the same way amounts are. However, they are incorporated into the overall balance equation using Pedersen commitments.
So they're part of that inputs-outputs fees equals zero check.
Precisely. The commitment math has to account for the fee to ensure the transaction balances correctly. And Monero's design also puts a lot of thought into the efficiency of storing and verifying all these cryptographic elements, the signatures, commitments, range proofs, to keep the system practical and usable.
Right, because all this complex crypto could make transactions huge or slow otherwise.
There's definitely a trade-off. Monero transactions are larger than, say, Bitcoins. But efficiency is a constant focus in development.
Okay, so we have these private transactions. How does Monero maintain the overall integrity of its ledger, the blockchain itself, and manage its money supply securely?
Well, fundamentally, Monero's blockchain works like most others in principle. It's a chronological chain of blocks. Each new block contains a batch of transactions and cryptographically references the previous block using its block ID, which is just a hash of the previous block's header.
Establishing that tamper-proof order of events.
Exactly. And to add new blocks and secure the network, Monero uses a proof-of-work consensus mechanism. The specific algorithm is called RandomX now, though it used to be kryptonite.
Proof of work, so miners are competing.
Yes. Miners use their computing power to repeatedly hash the block's data along with a random number, a nonce, until they find a hash result that falls below a certain difficulty target.
And this difficulty adjusts.
Constantly. The network automatically adjusts this target difficulty based on how quickly blocks are being found. The goal is to keep the average time between new blocks steady at around 120 seconds, or 2 minutes.
And RandomX, like kryptonite before it, was chosen for a specific reason, wasn't it? Something about mining hardware.
Yes, a very important reason.
Yeah.
It was specifically designed to be resistant to specialized mining hardware, particularly ASICs.
Why is ASIC resistance important?
It aims to keep mining more decentralized. If only specialized, expensive hardware can mine effectively, mining power tends to concentrate in the hands of a few large operations. By making the algorithm favor general-purpose CPUs, it allows more individuals with regular computers to participate in mining, hopefully leading to a more distributed and resilient network.
And if there's a disagreement, like a temporary fork in the chain,
The consensus rule is the longest chain rule, or more accurately, the chain with the highest cumulative difficulty. The chain that demonstrably represents the most computational work invested is considered the legitimate one by the network.
makes sense. Now, let's talk about the money supply itself. This is always a big topic. How does Monero manage its supply, especially given the privacy? How are new coins created?
That's a really interesting aspect of Monero. First off, it had no pre-mine.
Meaning no coins were allocated to founders or developers before the public launch.
Correct. All Monero in existence, or that will exist, is created through block rewards. These are new XMR given to the miner who successfully finds and adds the next block to the chain.
Okay, so miners get paid in new Monero. Do those rewards decrease over time?
Yes, initially the block reward amount followed a decaying curve, gradually decreasing as the total supply grew. This is common in many cryptocurrencies.
But Monero does something different long-term, right? The emission tail.
Exactly. This is a critical and somewhat unique design choice. Once the initial declining reward schedule finished, Monero transitioned to a perpetual fixed tail emission, meaning the block reward will never drop to zero. It's stabilized at a constant 0.6 XMR per block forever, which is 0.3 XMR per minute, given this 2-minute block time.
Why do that? Why not let the supply cap out like Bitcoin?
The rationale is long-term network security. In proof-of-work systems where block rewards eventually go to zero, miners would have to rely solely on transaction fees for income. There's a concern that this might not be enough incentive to maintain a high level of hashing power indefinitely, potentially making the network vulnerable to attacks.
So the tail emission guarantees a minimum predictable reward for miners forever.
Precisely. It ensures there's always a baseline incentive to secure the network through mining, contributing to Monero's long-term decentralization and security. It's a deliberate trade-off, infinite slight inflation versus potentially decreasing security over time.
That's a really thoughtful approach to long-term incentives. What about block size? We hear about block size debates in other chains. How does Monero handle that? Can blocks get too big or full?
Monero tackles this with a dynamic block size mechanism. It's not fixed.
How does that work?
There's a penalty system. If miners create blocks that are significantly larger than the median size of the last 100 blocks, their block reward gets reduced. This discourages miners from creating excessively large blocks just to collect more fees, helping to prevent blockchain bloat.
But it can grow if needed.
Yes. Crucially, the system allows the median block size itself to gradually increase over time based on network demand. So it balances the need to control bloat with the ability to scale naturally if transaction volume consistently rises.
Flexible, but with guardrails.
Kind of, yeah. And one last technical point on blocks. They use Merkle trees to efficiently organize all the transaction IDs within the block.
Merkle trees. Those allow for efficient verification, right?
Yes. And they also open up possibilities for future optimizations, like pruning. Nodes could potentially discard some old transaction signature data while keeping just the Merkle roots, which significantly reduces the storage space needed to run a node without compromising the ability to verify the blockchain's integrity. It's all about balancing privacy, security, and long-term scalability.
So there you have it. We've really unpacked quite a bit today. We've seen how Monero weaves together multiple layers of sophisticated cryptography.
Yeah, from those single-use addresses and powerful ring signatures.
To the Pedersen commitments hiding amounts and the range proofs preventing funny business.
All operating within this dynamic proof-of-work blockchain framework with things like tail emission and adaptive block sizes.
It really is a complete system, isn't it? Meticulously designed, it seems, from the ground up with one primary goal: maximizing financial privacy for its users.
Absolutely. It offers people a level of control over their financial footprint in the digital world that's pretty much unprecedented compared to transparent ledger systems.
This deep dive really highlights the incredible crypto engineering involved in trying to build a truly private digital currency.
It's a testament, really, to how innovative cryptography can be applied to solve these complex social and technical problems in completely new ways. It definitely creates a distinct paradigm for digital finance.
So the big question to leave you with, what does this all mean? Given Monero's advanced mandatory by default privacy features, what are the broader societal implications of having truly private digital transactions readily available?
Yeah, who ultimately benefits the most from this level of privacy? And conversely, what unique challenges does it introduce?
Thinking about existing financial systems, regulatory frameworks, how do they interact with something like this?
It definitely raises some fundamental questions.
Absolutely. It's definitely something for you to mull over as you consider the evolving landscape of digital currency and privacy.